Hello and a warm welcome to the Sleepy Narrator. I'm truly glad you've joined me this evening. Whether you're tucked under the covers with the lights dimmed low, letting your mind wander into the quiet, or simply easing your thoughts into stillness, this is your space. A soft corner of the universe where science drifts into lullaby. Tonight, we're beginning something a little special, a slow, unhurried journey into the deeper layers of reality. We'll wander gently through light and time, brushing the edges of thought, curiosity, and wonder. But our first step is something that appears simple: speed. More precisely, the speed that shapes all else. The speed of light. I've tried to make this moment deeply soothing. But if you find it a touch too fascinating, and your mind decides to stay awake a while longer in quiet wonder, well, there are worse ways to lose a bit of sleep, aren't there? And if this calm space already feels comforting, a gentle like on the video would be appreciated. You could even subscribe to keep this kind of stillness coming. For those who choose to support the channel through a super thanks or membership, thank you. Your kindness helps these calm journeys continue. Now, if you're settled, let's begin. Beyond your window, past the hum of walls and the shifting skies, something is always in motion. Not only planets and stars, but something more essential: light. It moves without steps, without wings. It needs no engine, no push. And yet it always travels at one unchanging pace. Not faster, not slower. Not even the immense pull of a black hole can make it move more quickly. It's as though the cosmos itself has raised a single sign reading, this far, no farther. The speed of light isn't just a number. It's a law, a boundary, a kind of universal rhythm. If space were a vast lake, light would be the quickest ripple that could ever move across its surface. Nothing else can outpace it. And that's odd, isn't it? In everyday life, speed feels flexible. You walk, you run, you pause, you watch things zoom past. A car can overtake a cyclist, a jet can surpass a bird in flight. We're used to movement stacking, one speed adding to another. But light refuses to follow that game. Picture shining a flashlight from the rear of a moving spaceship. You might think that since the ship is already racing forward, the light would travel even faster than normal. But it doesn't. Whether you're standing still or skimming near the edge of space in a rocket, the beam moves away from you at exactly the same pace, in every direction, no matter what. It's as though light refuses to take sides. Chase it as you might, it always slips just beyond your reach, not through cleverness, but because it's built into reality. Light never bends to your motion. Instead, space and time bend around it. To keep light's speed constant, the universe adjusts something else: your experience of time. The faster you travel through space, the slower you move through time. It's as if the cosmos maintains a quiet balance, shifting one aspect to preserve another. And here's where things begin to feel almost dreamlike. Imagine yourself aboard a train nearing the speed of light. You glance at your wristwatch. 1 second, 2 seconds, three. Everything feels normal. But to someone watching from outside, someone at rest, your watch ticks more slowly. Your heartbeat slows. Even your thoughts appear to drift more slowly. For you, time stretches out and you wouldn't even notice. You feel unchanged, yet outside, the world races ahead. This isn't fantasy. It's been measured and confirmed. Tiny particles in massive accelerators live longer when moving quickly. Clocks aboard satellites tick at slightly different rates than those on Earth. GPS technology takes this into account. The effect at our usual speeds is tiny, but it's always there. Why? Because light will not compromise. It's the anchor of the universe, unyielding. Everything else, even time itself, must adapt. Light becomes the canvas on which the patterns of space and curves of time are drawn. It's dizzying to think something as gentle and ordinary as light, the glow from a lamp or the shimmer on water, could hold such power over time's flow and the limits of speed. So, we realize this pace isn't just about motion. It's about structure, how the universe is built. The speed of light forms the very skeleton of reality. It not only limits travel but shapes cause and effect. It determines how information moves, what can be seen, what can be influenced, and how swiftly a signal can cross the stars. Without this limit, reality might unravel. Even now, lying still, light is touching you from the glow of a screen to the starlight, arriving across unimaginable distances. And though you feel still, you are in motion, spinning on Earth, orbiting the sun, drifting through the galaxy. The speed of light always defines the edges of what is possible. It's not a wall but a gentle boundary, a hush at the edge of reality. You don't need to chase it. It's already here in every flicker you see, in each breath warmed by sunlight, in every photon that brushed your skin today. But what if you could approach it? Get close enough to feel time slow in earnest. Could you see into the future? Step into a reality where time flows differently. And if at light speed time halts altogether, what then? Let's follow that thought. Light touches all things, warming your skin in the morning, tinting the sky blue, drawing leaves toward the sun and shimmering across rivers. You measure your hours by it, follow its trails through the seasons. But beyond its brightness and beauty, light has a deeper role. It shapes time itself, not just poetically but in the structure of the universe. Think again of that train, gliding near the speed of light. Inside, your breath settles, your thoughts move naturally, your heart beats as usual. Yet to an outside observer, your time unfurls slowly, stretching out like silk. A second for you might be many for them, and light is the reason. In the weave of reality, light's pace never changes. No matter how fast you go, light's speed holds steady. To maintain balance, the universe must adjust something else, and it chooses time. This isn't simply an oddity, it's a law. In Einstein's view, space and time are joined in a seamless flow called spacetime. Light moves through this union with perfect grace, setting the tempo. Everything else follows. If you could not just see light, but sense how it moves through this cosmic fabric, you'd notice time bending, slowing near mass, rippling under speed, shaped by the invisible landscape of spacetime. Light traces the terrain, revealing its curves. Picture yourself far from any star or planet in absolute stillness. You switch on a small beam of light. It travels straight into the black, linking your now with a future moment. That beam is a messenger, a bridge carrying information through time as much as space. And in a profound way, light doesn't just move through time, it carries it. Inside you, electrical signals ride on photons. Your sense of how long a second lasts, or how a memory plays out, is shaped by the pace of light. The most precise clocks, atomic clocks, use light to measure time with incredible accuracy, their lasers pulsing to mark moments with unfaltering rhythm. Nature's loyalty to this tempo is astonishing. Light from a star 100 million years ago still moves at the same speed today. It crosses vast distances unchanged, shaping the very structure of time along its journey. That ancient light reaches you now, connecting past and present. Your memories too are lit, each moment shaped by light entering your eyes, touching your brain, becoming part of you. Even in sleep, when the world darkens, light's influence lingers. Your body's rhythms, the rise of melatonin, the cycles of dreaming, are guided by it. You are, in many ways, made by light, but its role isn't merely biological, it's cosmic. Light keeps time meaningful, motion purposeful, causality intact. Without it, the story of the universe would dissolve into chaos. And so, as you rest, know that light cradles time itself. It shapes your seconds, lets you think in moments, and carries you gently from past to future. And this takes us to the next mystery. What happens when we move quickly enough to feel time truly bend beneath us? Even now, as you lie motionless beneath a quiet ceiling or a sky filled with dreams, you are never truly still. The earth spins beneath you, turning with calm persistence through night and day. Around the sun, our planet glides with a gentle tilt, drawing great circles that carry the seasons. The solar system itself drifts through the Milky Way like a lantern floating on a cosmic river, and the galaxy too is in motion, part of a slow, swirling dance with others far beyond what you can see. We are always moving, but motion is relative. And here begins one of the most unusual truths the universe has ever revealed. Time doesn't tick at the same pace for everyone. Not everywhere, not always. How it moves depends on how you move. Imagine a train sliding across a wide, open plain. You sit inside, watching the scenery pass, while someone outside stands still, watching you glide past in return. For both of you, the moment feels steady and real. But if you carried two clocks, perfectly tuned to light's rhythm, and compared them after the trip, you'd notice something extraordinary. The person on the train would have aged a tiny bit less. Not enough to notice, but enough to measure. This is time dilation, the slowing of time for something in motion, especially as it nears the speed of light. It's not just an idea. Scientists have measured it again and again. Particles racing through accelerators live longer than expected. Atomic clocks carried on fast aircraft tick a little more slowly than identical ones left on the ground. Time, it turns out, bends to movement. Why? Because in this universe, light speed must always remain the same. No matter how fast you are moving, you can't make light seem to go faster. So instead, the universe changes your time. It slows your seconds, stretches your minutes, all to keep that constant rhythm. This isn't a mistake. It's how reality balances itself. Let's look closer. Imagine you're aboard a spacecraft, smooth and quiet, drifting just under the speed of light. Inside, you sip tea, turn the pages of a book, or simply breathe. Your watch ticks. Your heart beats. Everything feels normal. But back on Earth, time is moving differently. What feels like 1 year for you might be 10 years there, or 50, or more. If you returned, you'd find a world transformed, cities rebuilt, languages evolved, people aged while you stayed almost the same. This isn't fantasy. This is special relativity, the real, measurable way time behaves at high speeds. It shows us that time isn't absolute, it's personal. Your journey changes how you experience it. The faster you go, the slower you age, not because time has stopped, but because you're moving through it differently. Think of time as a river. Most of us wade through it slowly, feet on the riverbed, the water moving evenly around us. But if you skim across its surface at incredible speed, you touch less of it. You're in the river for less time, even as you travel far. Your minutes stretch. Speed doesn't just move you through space, it carries you into a slower current of time. From your perspective, you'd notice no change. Your thoughts would flow normally. Your breath would rise and fall. Time dilation is invisible to you, like a deep ocean current unseen from the surface of a calm sea. Yet it's happening all the same. Even at the modest speeds of airplanes, we can detect it. The faster you move, the more you resist the ticking pace of the world around you. This is the universe's way of keeping order. It doesn't allow contradictions, no sending messages to the past, no breaking the chain of cause and effect. Instead, it adjusts your personal tempo so everything remains smooth and consistent. Humans didn't evolve to sense these shifts. We live at small speeds and short distances. But the cosmos always keeps the score, timing every beat with precision. You don't need to know the equations to feel the shape of it in your imagination. You can picture returning from a long journey to find the world changed beyond recognition. A child you knew could now be grown. A forest could have become a field, and you would have aged far less. In this way, speed becomes more than a measure, it becomes a way to hold on to time. Not through magic, not through myth, but through motion itself. Time is more flexible than it seems. Movement can cradle your hours more gently. Push fast enough, near enough to light, and you could leap into the future. You couldn't choose a moment like turning a page in a book, but you could bend the arrow of time around your path. You wouldn't escape time, but you'd ride it differently. This kind of time travel isn't about breaking rules. It's about discovering new ones. Even resting now, you're part of this dance. The stars above seem fixed only because they move with you. Time's flow isn't the same for all travelers. You're in a river, but not all parts of that river run at the same pace. And there's a famous story that shows just how strange this can become. A tale of two siblings, separated by speed, reunited by time, and changed forever. Picture two twins born seconds apart. They share the same expressions, the same childhood, the same unfolding years. Their lives run side by side, almost in perfect rhythm. Until one day, one leaves not across a city or an ocean, but far into space. The traveling twin boards a sleek ship and launches outward, gliding near the speed of light, skimming the dark like a feather caught in a quiet breath of gravity. While this twin travels, the other stays behind on Earth, walking through familiar days. Decades pass here, forests grow and fall, oceans shift, children become parents. But on the ship, life is slower. The heart still beats, thoughts still flow, but the seconds are stretched thin. The body ages less. This is the twin paradox, a real, testable result of special relativity. When the traveling twin returns, they are younger than the one who stayed behind. The difference could be small or immense, depending on the speed and duration of the trip, but it is real. The twin in motion has taken a different route through time itself. Motion changes time's flow. The twin on Earth remains within one frame of reference, still relative to the planet. The other enters a frame where time moves more slowly. Both experiences are valid to the universe, but they don't share the same rhythm. The difference isn't noticed until they meet again, face to face after all those years. Both feel they lived every moment naturally, yet one has aged less. This is the heart of the paradox. By moving so fast, one took a shorter path through time. It's not science fiction. Even astronauts orbiting Earth, moving at a fraction of light speed, experience this on a tiny scale. Their clocks tick just a little more slowly. They return a whisper younger than they would have been. At greater speeds, that whisper becomes a clear voice. This means time isn't a rigid, universal clock hanging over the cosmos. It bends, stretches, and folds depending on your journey. Each person carries their own version of time, wrapped around them like an invisible cloak, changing with every step. When you move fast enough, your rhythm becomes entirely your own. The twin paradox lets us feel this time as a fabric, not a fixed line. And there's something poetic in it. That aging isn't only about years or candles, but about movement, about how you flow along the river of time. Even if two lives begin together, they may drift through the years in beautifully different ways. So tonight, as you rest, think of the twin inside your thoughts, one that stays and one that ventures far, one that lingers in the present and one that races toward the edge of light. And imagine what it would be like to travel so fast, so far, that time itself could barely reach you. Float with me for a moment. Let your body feel light, as though you're hovering just above the surface of some quiet world, maybe a gentle blue planet, maybe a rocky moon far from here. There's no sound, only stillness. And in that stillness, something begins to shift. Not your breath, not your heartbeat, but time. It slows, softly and subtly. The deeper you sink into gravity's pull, the more gently your seconds stretch. You wouldn't notice it at first, but the clocks would. A clock near your feet would tick just a bit slower than one above your head. A satellite far overhead would feel time move just a little faster than you do down here. It sounds impossible, and yet it's real. Gravity bends more than just your path. It bends time itself. This quiet, strange truth is one of the great discoveries of general relativity. Massive objects, planets, stars, black holes, pull not only on space, but also on the flow of time. Picture time as a fabric stretched across the cosmos. Wherever there's mass, that fabric dips and curves. The heavier the mass, the deeper the dip. And near those curves, time begins to slow, not break, not reverse, but soften, as if drawn out by unseen hands. Even here on Earth, this happens. Your head ages just a tiny bit faster than your feet. You won't feel it, but atomic clocks can detect it. Satellites must account for it. Your phone's GPS relies on it. The closer you are to gravity's center, the more gently time moves. It's like standing in a deep valley of time, watching the flow slow compared to the hills above. Now imagine deepening that valley. Pull it tighter, make it heavier. Picture standing near a neutron star, a collapsed core with unimaginable weight. Here, gravity's pull is so strong that minutes for you might pass while hours pass for someone far away. You are wrapped in gravity's arms and time moves with you. And if you approached a black hole, the most extreme gravity in the universe, you'd find the deepest well of all. So deep, so heavy, that time itself almost freezes at its edge. Someone watching you from far away would see you slow, then stop, suspended forever at the event horizon, the point beyond which not even light escapes. But from your perspective, time would continue as usual until it didn't. Beyond that edge, time and space swap roles. Directions twist. The arrow of time turns inward toward something unknown. Let's step back to the gentler curves, the soft dips made by planets and moons. Even here, time is shaped by gravity. Every mass leaves an imprint, every orbit creates a ripple. Time is not a straight road but a winding path drawn by gravity's hand. This is why satellites need corrections, why physicists carry clocks up mountains, why astronauts return a fraction younger than those who stayed behind. Mass tells spacetime how to bend, and bent spacetime tells clocks how to tick. You can't feel this bending, but it's always there. You're not sitting on something fixed. You're resting in a bowl carved into the fabric of time. Gravity isn't just pulling you down, it's stretching your seconds. The universe is not a flat, empty stage. It's alive with folds and curves, valleys and hills shaped by the weight of stars. Time runs like water through this landscape, with gravity guiding its course. Right now, as you lie still, you're floating on one of these quiet curves in time. And speed isn't the only thing that can stretch time, gravity can too. They are partners in the same dance, pulling at the same invisible thread. When both rise to extremes, time becomes delicate, fragile. And no place shows this more clearly than the edge of a black hole, where light struggles to leave and time itself hesitates. Drift with me there. Far beyond the planets, past the scattered dust of forgotten comets, lies a stillness where even starlight begins to fade. Ahead is something unlike anything else. At first, it looks like nothing at all, a darkness so deep it feels like absence. But it's not empty. It's one of the most mysterious, powerful places in existence, a black hole. You approach slowly. There's no pull at first, no sound, no rush, just a thickening silence. Black holes are born from collapse. When a massive star uses up its fuel, it can no longer push back against its own gravity. It falls inward deeper and deeper until it becomes infinitely dense, a singularity. The mass of many suns is packed into a space so small it defies comprehension. Around it, spacetime curves so sharply that nothing can escape. Not matter, not energy, not even light. And with light trapped, time itself is trapped too. As you approach, time stretches, not like a lazy afternoon but in its very structure. Moments lengthen. They resist the next. To an observer far away, you appear to slow, to move less and less, until just before crossing the event horizon, you seem frozen, never quite reaching the edge. But from inside your own perspective, you keep moving. You pass the horizon in what feels like an ordinary moment. Inside, the paths of space and time twist into something unrecognizable. The arrow of time turns inward, and every path leads to the singularity. The singularity isn't a place so much as a moment, the unavoidable future for anything inside. You cannot turn back. You cannot pause. Time ends there. No one knows what truly happens at that core. Our mathematics breaks down. Perhaps there's new physics hidden there. Or perhaps nature keeps some secrets folded away forever. For now, you hover at the edge. Light struggles upward but fades into deep red before vanishing. Clocks near the horizon tick slower than yours. Space tugs not just on your body but on your seconds. Here, time doesn't end violently, it unravels gently. Space and time blur together. They fold inside out. Black holes aren't flaws in the cosmos. They're windows into how the universe behaves under the most extreme conditions. They teach us that time can slow almost to a stop. That light can stretch until it can't rise. That gravity at its most intense doesn't just pull, it rewrites the story of reality. Picture it now. A black sphere set among the stars, a place where time holds its breath. Past and future meet at its curved edge. And if time can bend this far, maybe it isn't just a straight line, maybe it's a landscape, filled with valleys, ridges, and deep ravines carved by speed, mass, and energy. Let's begin to see time not as a ticking clock, but as a terrain we move through. Picture galaxies swirling in valleys of spacetime. Imagine massive black holes forming deep wells where time hardly moves. Think of light weaving through these curves, always following the shape of the land beneath it. This is the heart of general relativity, Einstein's vision of spacetime as a living fabric that can bend, ripple, and wave. When two black holes collide, they send ripples through spacetime, gravitational waves that spread across the cosmos, gently changing distances as they pass. We've heard them now, with instruments so sensitive they can feel the shiver of spacetime itself. As you drift tonight, let go of the idea of time as a rigid line. Instead, feel it as something you move through, like a meadow, like a dream. Let it rise and fall, slope and curve. Realize that you are a traveler in a landscape that shifts constantly around mass, motion, and energy. You aren't walking a fixed road. You're wandering a field of moments, and the ground beneath you is alive. Let's move from the extreme pull of black holes to something gentler, though no less mysterious. The quiet, constant speed of light is not just a limit for how fast we can travel. It's also the speed at which every piece of information in the universe moves. Think of it like this. When you look at the moon, you're not seeing it as it is now, but as it was about a second ago. Light takes time to travel, even over short distances. The further away something is, the older the light we see. In this way, space is a kind of time machine, but one that only looks backwards. When you gaze at the sun, you're seeing light that left it roughly 8 minutes ago. If the sun were to vanish suddenly, impossible though that is, you wouldn't know until those 8 minutes passed. And when you look at a distant star, you're often seeing light that left hundreds or thousands of years before you were born. This means that every star-filled sky is also a history book. Every photon is a messenger, carrying not just energy but a record of the moment it left its source. Some of the light reaching your eyes tonight began its journey long before humans existed, traveling without pause across the vacuum, untouched by anything that might slow it. The further out we look, the deeper into the past we see. And because light speed is fixed, there is a limit to how far we can see, not just in space but in time. That limit is the edge of the observable universe, about 46 billion light-years away. Beyond that, light hasn't had time to reach us since the universe began. The speed of light ties space and time into one fabric, spacetime. Moving through space changes how you move through time, and the flow of time shapes how you experience space. Light travels along this fabric perfectly, following its curves, never faster, never slower. It's easy to think of light as a thing, a beam, a wave, a particle, but it's also a boundary. It marks the edges of what can be known, what can be reached, and what can be changed. Nothing can send a signal faster than light without bending cause and effect in dangerous ways. This limit isn't there to frustrate us. It's there to keep the universe consistent. If you could somehow travel faster than light, you could, in theory, send a message into your own past. That sounds like a dream for storytellers and a nightmare for reality. It would break the chain of events, allowing effects to happen before causes. The universe appears to forbid this, holding tight to the speed of light as a safeguard. But what about moving close to it? That's where things get strange in ways we've already seen. Time slows, distances shrink, and reality begins to warp in ways our everyday senses can't detect. The faster you go, the more space and time bend around you. Imagine you're on a ship accelerating toward light speed. At first, the stars drift by slowly, as if you're walking through a park at night. Then, as your speed increases, they begin to blur and shift. Light ahead of you blue shifts, becoming brighter and more energetic. Light behind you red shifts, fading into longer, softer wavelengths. The universe in front of you seems to crowd closer, while the space behind stretches away. This isn't an illusion, it's the way spacetime itself responds to your motion. From your perspective inside the ship, you're moving normally. But to an outside observer, you've become a different kind of traveler. Your seconds are longer, your meters are shorter, and your path through time is unlike theirs. And if you could reach light speed exactly, which no object with mass can, time for you would stop altogether. Every point along your path would collapse into a single instant. From light's perspective, if we can even imagine such a thing, the entire journey from start to finish happens at once. There is no before or after. This is part of why light is so strange. It doesn't experience time in the way we do. A photon born in the heart of a star and absorbed in your eye has, in its own frame, never aged at all. It simply existed in one moment and then in another without any separation. But we are bound to slower speeds, and so we live inside time, moving from one second to the next, unable to skip ahead or stand still. Yet by traveling faster, we can stretch those seconds, bending them to our journey. This is where the idea of time travel into the future becomes more than science fiction. It's not about finding a machine with spinning lights and brass levers. It's about speed. Push close enough to light's pace, and you leave the rest of the world behind. You could return minutes older while decades pass for those who stayed. The catch, of course, is that reaching such speeds takes immense energy, more than we can currently produce for a craft carrying people. But in principle, nothing in physics forbids it. If we could solve the problem of propulsion, we could ride time's river into the future. Now imagine coupling speed with gravity. In the presence of massive objects, time slows. Near a black hole, it slows to a crawl. If you could orbit close to one, safely outside its event horizon, you could spend a short time there and return to find that centuries had passed elsewhere. This is the dream of the twin paradox made real. You wouldn't be able to go into your own past, but you could step far into someone else's future. And this isn't only theory, it's built into the same physics that guides our satellites and deep space probes. Everywhere in the universe, light speed is the thread weaving these effects together. It links gravity to time dilation, motion to the shrinking of distances, space to the history of what we see. Even when you stand still, you are wrapped in light's influence. The photons hitting your skin, bouncing from the walls and flowing from the sun, are part of the same framework that defines the shape of your life in time. The clock on your wall and the glow in the night sky both follow the same rule. The speed of light is not simply a number in physics, it's the backbone of reality. And by understanding it, we begin to see time itself not as a fixed march forward, but as a landscape we can shape, stretch, and explore. So tonight, as you rest, imagine yourself a passenger on a ship that can dance just beneath that speed, close enough to feel time shift beneath your feet, slow enough to return with stories of a future no one else has seen. Imagine the stars crowding closer ahead, the universe stretching softly behind, and the hum of spacetime carrying you forward like a lullaby. For now, you drift here, where time moves at its ordinary pace. But the river has many currents, and some run far swifter than we can yet follow. One day, perhaps, we'll learn to ride them. We've seen how speed and gravity bend time, how light defines the limits of what can be known, and how the cosmos keeps a careful balance between movement, causality, and the flow of moments. But there's another side to this, a more delicate, almost poetic truth, that time itself is not something the universe hands out evenly. It's personal. Your time is not my time. It's not the time of the planet orbiting two stars hundreds of light years away, nor the time of a comet sailing in the deep cold between galaxies. Time belongs to the frame you're in, the place, the speed, the gravity around you. And when those change, time changes with them. Think about the signals that guide your life. Every second, photons are carrying information to you. They tell you what's around the next corner, how the sky is changing, and how the world moves. All of these signals obey the same rule. They never travel faster than light. This single fact shapes not only what you can see, but when you can see it. If something happens far away, you only learn of it after light, or another form of signal reaches you. That delay means the present you experience is already the past for the thing you're looking at. Even the reflection in a mirror is a tiny bit old, because light needed time to bounce from your face to the glass and back. At small distances, those delays are too quick for you to notice, but across vast stretches of space, they are everything. A galaxy 10 million light-years away appears as it was 10 million years ago. Its present moment is hidden from you until the light has had time to travel. The deeper into space you look, the deeper into history you are. This is why telescopes are also time machines. The James Webb Space Telescope, for example, doesn't just see far, it sees ancient light, light that has traveled for billions of years. By capturing it, we glimpse a universe that no longer exists in that form. The galaxies we see may have merged, scattered, or died long ago, but the light still carries their younger image to us. Light's constancy lets us measure cosmic history. Its speed is the same everywhere, no matter where you are or how you move. This gives us a ruler for both space and time. Astronomers use it to gauge distances, to measure how fast the universe expands, and to map the silent echoes of its earliest moments. But it also sets a limit, one we cannot cross. If you want to change something, you must reach it before it happens. Light ensures you can't act on an event faster than the time it takes for that event's information to reach you. This keeps cause before effect, holding the arrow of time steady. It's tempting to wish for a way around this, a shortcut that lets you skip ahead. Science fiction is full of them. Wormholes, warp drives, instant teleportation. These ideas borrow from real physics, but always with some obstacle that stops them from breaking the deeper rules. A wormhole, for example, could theoretically connect two distant points in spacetime, letting you step instantly from one to the other. But to hold one open without it collapsing might require exotic matter, a substance we've never found and don't know how to create. Even if it were possible, wormholes might still obey the same restrictions on causality that light enforces. Warp drives, like the one imagined by Miguel Alcubierre, bend spacetime itself so that a ship rides inside a bubble, with space expanding behind it and contracting ahead. In this way, the ship never moves through space faster than light, but the space around it does. It's an elegant idea, but one that may demand more energy than exists in the observable universe. These possibilities remind us of something important. The speed of light isn't just a number, it's the shape of reality. Any path we imagine must fit within it, or work by bending the structure of space and time themselves. And yet, even without breaking the limit, we can still play with time. We've already seen how speed can slow your seconds and how gravity can do the same. Combined, they give us a way, at least in theory, to move far into the future. Picture this: a journey to the heart of a galaxy toward a supermassive black hole. Your ship orbits just outside its event horizon, where gravity is fierce but survivable. Every hour you spend there might equal years or centuries elsewhere. Then you leave, drifting back into calmer space. You'd return to find the universe older, history rewritten without you in it. This is not just speculation. The same physics is tested every day. Satellites must adjust their clocks for both gravitational and velocity-based time dilation. If they didn't, GPS systems would drift by kilometers in just a day. The equations Einstein wrote over a century ago quietly guide your phone's map as you walk down a street. And that is perhaps the most grounding truth in all of this. The bending of time is not just a distant, cosmic effect. It's here, woven into your every step, every message, every glance at the sky. You live inside relativity's rules even if you don't feel them. It's easy to think of time travel as something grand, a leap through centuries, a blur of spinning lights, a door into another era. But in a way, you're already doing it. Every moment you spend at a different height, speed, or gravity than someone else is a moment where your time and theirs part ways, however slightly. You may never notice, but the separation is there, recorded in the silent bookkeeping of the cosmos. In this light, the future is not something waiting in one single place. It's unfolding differently for every point in the universe, every traveler, every grain of dust drifting through a sunbeam. You can't see it all at once, but you are a part of it, carrying your own small slice of time forward. So as you rest now, picture yourself floating in that slice, a bubble of your own seconds, shaped by the speed and gravity around you. Others are drifting too, each in their own bubble. Sometimes they move together, sometimes they part, but all are carried forward by the same quiet rule: nothing outruns the light. That rule may seem like a limit, but it is also a gift. It keeps the story of the universe moving in one direction. It preserves the threads that bind cause to effect. And in doing so, it allows us to trust the ground we walk on, even when that ground is the fabric of time itself. In the stillness of night, it's easy to imagine time as something smooth and unbroken, a steady flow from the past through the present and into the future. But the more we explore the universe, the more we realize this image is far too simple. Time doesn't run the same way for everyone, and in some corners of reality, it behaves in ways that defy common sense. Take the expanding universe itself. When we look at distant galaxies, we see their light stretched into longer wavelengths, a phenomenon called redshift. This happens because space is stretching between us and them. It's not that the galaxies are rushing through space away from us. It's that space itself is expanding, carrying them with it. The result is profound. The further away a galaxy is, the faster it seems to be receding. Some are so far that the space between us grows faster than light can cross it. That doesn't mean they're breaking the cosmic speed limit. The speed of light still holds locally. But it does mean their present state will forever be out of our reach. This expansion has another strange consequence. It changes how we measure time across the universe. In the early cosmos, everything was closer together, and light took less time to travel between points. Today, as space stretches, that same journey takes longer. The very fabric of time is tied to the growth of space. If we could stand outside the universe, which of course we cannot, we might see its history all at once, from the first flicker after the Big Bang to the spread of galaxies into the cold darkness billions of years from now. But from within, we can only move forward, feeling time shaped by the changing geometry of space. Cosmic expansion is a reminder that time is not only personal, it's also collective. The age of the universe is measured relative to the flow of time experienced by matter moving with the expansion. For us, that age is about 13.8 billion years. But in regions of extreme gravity or motion, that number might be experienced differently. There's another way the universe reminds us of time's complexity, through the faint afterglow of the Big Bang. This light, known as the cosmic microwave background, has traveled for nearly the entire age of the universe to reach us. It comes from a time when the cosmos was young and hot, just 380,000 years old. In studying it, we are not just looking back in time, we are touching the edge of the observable past. Every photon in that ancient glow has moved at the speed of light without pause. Yet because the universe has expanded around it, its wavelength has stretched into the microwave range. The light is older than any mountain, any planet, any star we know, and it carries a record of how time and space have unfolded together. The cosmic microwave background also reminds us of something subtle. The speed of light doesn't just limit how fast we can go, it shapes the history we can access. We will never see beyond the moment when the universe became transparent to light. Before that, space was filled with a dense plasma that scattered photons in all directions. The earliest times are hidden from us except through other messengers, like gravitational waves or the distribution of matter today. And yet, these limits are part of what makes the universe readable. Without them, events might blur together with no order, no way to distinguish cause from effect. The boundaries light creates give us structure, a way to map where and when things happened. Now, think again of your own place in this structure. You are a point in spacetime, surrounded by an observable sphere, defined by the distance light has traveled since the universe began. Everything inside it is part of your visible past. Everything outside is still invisible future light, on its way toward you. That sphere grows as time passes, but it will never include certain distant galaxies because the expansion of space is carrying them away too quickly. This means your observable universe is unique to you. Someone on a planet a billion light years away would see a different slice of the cosmos, with different events in view. No one has a complete picture. We are all seeing different pages of the universe's history. It's a humbling thought and a hopeful one. Even in our limited view, we can uncover the deep patterns that govern everything. We can watch galaxies spin, measure the pull of gravity, and trace the slow growth of cosmic structures over billions of years. We can see the fingerprints of dark matter in the way galaxies cluster, and the fingerprints of dark energy in the accelerating expansion. Dark energy, in particular, holds one of the great mysteries about the future of time. If it continues to push space apart faster and faster, there will come a distant era when most galaxies slip beyond our horizon. Their light will never reach us again. The night sky will grow emptier, not because stars are dying, but because the light of most of them will be permanently out of reach. To future observers in that time, the universe may appear still and small, with no hint of the vast structures we see today. The evidence of cosmic history will fade, and time will seem simpler, but only because so much of it has been hidden away beyond the edge of sight. This is the quiet tragedy and beauty of cosmic time. It is always changing what we can know. The further we go, the more of the past we lose, even as we move toward the future. It also means that in a sense, time is a resource. Right now, the sky is rich with light from billions of galaxies. Right now, we can map the cosmic web and trace it back to its beginnings. But this era will not last forever. There will come a time when the sky grows dark, not from the absence of stars, but from the stretching of space itself. In this way, we live in a privileged moment, a moment when the history of the universe is still written brightly across the sky. We can still read it, we can still learn from it, and perhaps that's the deepest truth about time. It's not only something to measure or travel through or slow down, it's something to witness. The patterns of time in the turning of planets, the life of stars, the growth of galaxies, are stories unfolding all around us. Each is fleeting. Each is shaped by motion, gravity, and the finite speed of light. As you drift toward sleep tonight, imagine the observable universe as a bubble around you. See the light streaming in from its edges, carrying messages from across billions of years. Imagine holding that light in your hands, feeling the warmth of ancient stars, the whisper of galaxies long gone. That light is your share of the universe's story, your portion of time's great ocean. And know that, for as long as you are here to see it, you are part of that story too. We've been traveling through the layers of time, the bending caused by gravity, the stretching from speed, the limits set by light, and the vast history written in the sky. But there's another truth that sits quietly behind all of this. Our understanding of time is still incomplete. Einstein's theories tell us how time behaves in the presence of matter, energy, and motion. They explain the slowing of clocks near gravity wells, the way moving fast can stretch seconds, and how light acts as a cosmic speed limit. These ideas have been tested again and again, from laboratory experiments to spacecraft navigation, and they work flawlessly in every case. But there's a missing piece: the link between relativity and the other great pillar of modern physics, quantum mechanics. Quantum theory describes the smallest scales of reality, where particles behave like waves and probability rules instead of certainty. Here, time doesn't quite act the same as it does in relativity. At the quantum level, events don't always have a simple before and after. Particles can be in superpositions, existing in multiple states at once, until measured. Entangled particles can affect each other instantly over vast distances, a phenomenon Einstein himself called spooky action at a distance. It doesn't let us send information faster than light, but it challenges our sense of how cause and effect should work. When we try to combine quantum mechanics with general relativity, something breaks. The smooth fabric of spacetime in relativity doesn't match the restless, uncertain behavior of quantum fields. At scales smaller than a proton, our equations collapse into infinities. This is especially troubling when we think about black holes. According to relativity, anything that falls into a black hole is lost forever, including all the information about its original state. But quantum mechanics insists that information cannot be destroyed. The clash between these rules creates what's called the black hole information paradox, a puzzle that has driven physicists for decades. Some believe the answer lies in quantum gravity, a yet undiscovered theory that unites the large-scale structure of spacetime with the tiny-scale behavior of particles. Ideas like string theory and loop quantum gravity are attempts to bridge this gap, suggesting that spacetime itself might be made of tiny, discrete building blocks, or that additional hidden dimensions could shape its behavior. If such a theory is found, it could change our understanding of time entirely. Perhaps time is not continuous, but granular, flowing in tiny, indivisible ticks. Perhaps it's not even fundamental, but an emergent property, something that arises from deeper laws we don't yet see, much like temperature emerges from the motion of molecules. Some physicists even suggest that time, as we experience it, might be an illusion, a byproduct of how our brains process change. The universe at its deepest level might be timeless, with all events existing together, and our sense of motion through time coming from how we perceive them. It's a dizzying thought, but one worth holding for a moment. If past, present, and future all exist equally, then in some sense, every moment of your life is still out there, in spacetime. The child you were, the person you are, and the person you'll become are all fixed within the four-dimensional fabric. You are simply experiencing them in sequence. From this view, time travel into the past might not mean changing events, but visiting a part of the spacetime landscape that's already there. The problem, of course, is getting there. Relativity's equations allow certain spacetime geometries, like rotating black holes or wormholes, where closed loops in time might exist. But such conditions may be unstable or require forms of matter that cannot exist in our universe. Still, the possibility lingers. Even if it proves impossible in practice, exploring it sharpens our understanding of the rules. Every question about time, whether it's about the ticking of a clock in orbit or the fate of a star collapsing into a black hole, pushes us closer to the underlying truth. And perhaps that truth will surprise us in ways we can't imagine. Consider how strange relativity must have seemed when Einstein first proposed it. That time could slow, that simultaneity could vanish depending on your motion, that gravity could curve the very stage of the universe. What will seem just as strange to us 100 years from now? For now, we live in the middle ground between the vast and the tiny. We can feel the pull of gravity on time, see the stretching of light from galaxies, and measure the drift of atomic clocks on mountaintops. But we can't yet see the quantum grain of spacetime or the full picture of how the universe keeps its record of events. This is part of the beauty of science. It's never complete. Every answer opens new questions, and time, the thing we're trying to understand, keeps moving while we work. When you think about it this way, the study of time is also a study of ourselves. We are creatures who live in the present, remember the past, and imagine the future. We build tools to measure moments more precisely than nature ever intended, from sundials to atomic clocks that would lose less than a second over the age of the universe. We build telescopes to look back billions of years, and particle accelerators to probe the smallest slivers of a second. We send spacecraft to test relativity in the emptiness between planets. All of it is part of the same human desire, to know where we are in the grand unfolding of moments. So as you rest tonight, consider the possibility that time is larger, stranger, and more flexible than we've ever thought. Perhaps it is a thread we can follow through the fabric of the universe. Perhaps it is a tapestry we can step back from and see whole. Or perhaps it is something we carry with us, a personal rhythm that moves through the grand symphony of spacetime. Whatever the answer, one thing is certain. The more we learn about time, the more it teaches us about the universe and about ourselves. If time is a river, then every traveler moves through it at their own speed, guided by the shape of space and the weight of gravity. But like any river, it has currents and eddies, places where the flow changes, slows, or bends. And for all our science, we are still learning where those currents lead. One of the most intriguing possibilities for altering the path through time lies not in speed or black holes, but in the geometry of spacetime itself. In Einstein's equations, spacetime is flexible. It can stretch, twist, ripple, and fold. And in certain rare solutions, it can create paths that loop back on themselves. These loops, called closed time-like curves, are theoretical pathways that could allow a traveler to return to their own past. They aren't pure fantasy. They arise naturally in some exact solutions to general relativity, such as the spacetime around a rotating cylinder of infinite length, or within the throat of certain wormholes. But these solutions come with enormous problems. A rotating cylinder the size and density needed to create such an effect is far beyond anything that could exist in nature. And wormholes, while allowed in theory, would collapse under their own gravity unless held open by a form of negative energy we have never observed. Even if they could exist, there's the problem of paradoxes. If you could return to the past and change an event that led to your own journey, you create a loop of cause and effect with no clear beginning. The grandfather paradox, the idea that you could prevent your own existence, is the most famous example. Some physicists argue that nature prevents such contradictions through a principle called chronology protection. This idea, proposed by Stephen Hawking, suggests that the laws of physics will always act to prevent time loops large enough for macroscopic travelers. Quantum fluctuations, for example, might destroy a wormhole before it could be used for backward travel. Others take a different view, suggesting that closed time-like curves could exist, but that they would always resolve paradoxes in a self-consistent way. In this view, anything you do in the past was always part of history, so you cannot truly change it, you can only fulfill it. A third possibility is that time travel to the past would create branching timelines. In this multiverse interpretation, each change spawns a new, separate history, leaving the original untouched. You would not be altering your own past, but creating a parallel one. For now, these remain in the realm of theory, because nothing in our current technology allows us to manipulate spacetime on the scale needed for such travel. But exploring the math forces us to confront the limits of what time means, and how flexible those limits might be under extreme conditions. The study of time isn't limited to such grand possibilities. It also appears in the smallest, most precise measurements we can make. Atomic clocks, for example, are now so accurate that they can detect the difference in time between your head and your feet while you're standing. The higher a clock is above Earth's surface, the weaker the pull of gravity on it, and the faster it ticks. This isn't just a curiosity, it has practical effects. GPS satellites orbit high above the Earth, where gravity is weaker and their speed is greater than ours on the surface. Both effects cause their clocks to run at a slightly different rate than ours. Without constant adjustments, GPS navigation would be useless within a day. Time dilation is also measured in high-energy particle experiments. Muons, short-lived particles created when cosmic rays hit the atmosphere, decay in microseconds. But when they're moving near the speed of light, their internal clocks slow down, allowing them to survive much longer from our perspective. This is not theory. It's observed every day in particle accelerators. These experiments are small-scale versions of the same effects that, in theory, could allow humans to travel into the far future. They remind us that time dilation is not exotic science fiction. It's a natural consequence of how the universe works. But as much as we can measure, there are still mysteries that resist our tools. One of the deepest is the arrow of time, the fact that events seem to move in one direction, from past to future, even though the fundamental laws of physics work equally well in reverse. Why do we remember the past but not the future? Why does a dropped cup shatter instead of reassembling itself? The answer seems tied to entropy, the measure of disorder in a system. The second law of thermodynamics states that in an isolated system, entropy tends to increase. This creates a direction for time, from states of lower entropy to higher. The universe began in a state of extremely low entropy, and ever since, it has been moving toward higher disorder. Stars burn their fuel, galaxies spread apart, heat flows from hot to cold. This overall increase in entropy gives us the arrow of time we experience. But why did the universe start in such an ordered state? This is one of the great puzzles of cosmology. Some theories suggest it's a consequence of inflation, the rapid expansion that took place in the first fraction of a second after the Big Bang. Others hint that our universe might be one cycle in an endless sequence, with each cycle beginning in low entropy before running forward again. Whatever the cause, entropy's growth means the universe is moving toward a heat death, a state in which all energy is evenly spread and no work can be done. In that distant future, time may lose its meaning altogether because nothing will change from one moment to the next. This is a sobering end to picture, a universe gone cold and still, with no stars, no motion, no life. But it is also unimaginably far away, perhaps tens of trillions of years beyond the current age of the cosmos. For now, the universe is vibrant, full of energy flows and processes that mark the passage of time. And in the present, time is ours to explore, measure, and perhaps even manipulate. Every observation we make, from the slowing of clocks in orbit to the stretching of light from distant galaxies, deepens our understanding of this most elusive dimension. So as you close your eyes tonight, imagine the flow of time not as a straight line but as a landscape, with valleys where gravity slows it, ridges where speed stretches it, and perhaps hidden tunnels that loop it back on itself. Somewhere in that landscape, your own path winds forward, shaped by the physics of the universe and the choices you make within it. In that sense, we are all time travelers already, carried into the future at the steady pace of 1 second per second, unless we find a way to steer. When we talk about time travel, we often imagine vast distances covered in the blink of an eye, or stepping out of a machine into an era centuries removed from our own. But the truth is that our real journey through time is constant, unbroken, and deeply personal. Every heartbeat carries you forward. Every breath marks another instant in your own timeline. Yet this steady march is shaped in ways you may not feel by the pull of gravity, the speed of your motion, and the structure of the universe itself. These forces work quietly, adjusting the flow of time without your awareness. In our everyday lives, these effects are so small that we need the most sensitive instruments ever built to measure them. But in extreme conditions, they become impossible to ignore. Imagine orbiting close to a neutron star, a sphere only a few kilometers wide but more massive than our sun. The gravity would be so intense that time for you would slow dramatically compared to someone far away. You could spend hours there, only to return and find that years had passed elsewhere. This slowing of time is not a trick of perception. It's a real, measurable difference in the passage of events. Clocks near massive objects tick more slowly than those farther away. The same is true for objects in motion. The faster you move, the slower your time runs compared to those at rest. These are not separate effects but two sides of the same coin, both described by Einstein's relativity. Together, they form a toolkit for bending time, even if our current technology can't yet take us to the extremes needed for dramatic jumps into the future. Still, the universe provides us with natural laboratories to study these effects. Black holes, neutron stars, high-energy particle beams, each shows us the flexibility of time's flow. We can watch stars orbiting close to the supermassive black hole at the center of our galaxy, and see the redshift of their light as gravity stretches their seconds. We can track particles in accelerators surviving far longer than they should, because their near-light speed motion dilates their internal clocks. These experiments confirm something remarkable. The laws of physics do not privilege any one clock over another. Time is local. Each observer measures it according to their own frame of reference, and each measurement is valid. There is no universal now that applies everywhere at once. This challenges our everyday sense of reality, where we assume events happen in a single shared present. But in spacetime, what is now for you may be past or future for someone moving differently or living elsewhere in the cosmos. The idea of simultaneity, of two events happening at the same moment, is not absolute but relative. From this perspective, the universe is a vast network of timelines, each woven from the experiences of an individual observer. These timelines may intersect, diverge, and overlap, but they are never identical. The moment you share with a friend is a point where your paths align briefly, before each continues on its own course. The relativity of time becomes even more striking when we think about light. Because it travels at the maximum speed allowed by the universe, light defines the structure of causality, the order of cause and effect. If two events are separated by more distance than light can cross between them, there is no way for one to influence the other. This boundary, called the light cone, marks the limit of possible interaction. Your entire life exists inside a growing light cone. Everything you can affect lies within your future light cone, and everything that can affect you lies within your past light cone. Outside of these cones are events forever beyond your reach, no matter how far into the future you go. This framework preserves the consistency of the universe. No matter where you are or how you move, the speed of light and the limits it creates remain the same. It's the reason we can trust that cause comes before effect, and that history unfolds in a coherent way. At least, it does most of the time. Quantum mechanics complicates this picture in subtle ways. At the smallest scales, particles can appear to influence each other instantly through entanglement, even when separated by large distances. But these correlations can't be used to send messages faster than light, so the broader structure of causality remains intact. What's fascinating is how relativity and quantum mechanics, despite their differences, both point to a universe where time is not the rigid, uniform flow we once imagined. Instead, it is elastic, personal, and intertwined with space itself. And this brings us back to the question so many people ask: could we ever travel to the past? From what we know, it's extraordinarily unlikely. The solutions that allow it require conditions: infinite cylinders, stable wormholes, negative energy, that we have no evidence exist. Even if they did, the paradoxes of changing the past would demand a new understanding of how reality protects itself from contradictions. But the future, that is open to us, at least in theory. By moving close to the speed of light or spending time near intense gravitational fields, we could slow our personal time enough to leap forward in history. The challenge is not in the physics but in the engineering, finding the energy and technology to reach those extremes safely. Until then, we remain bound to the slow path, carried forward 1 second at a time. Yet even here, we can use our understanding of time to navigate the universe more effectively. From the synchronization of global communications to the navigation of spacecraft across millions of kilometers, we already rely on relativity in ways that would have seemed magical a century ago. Time is not just a background for our lives, it's an active player in the structure of reality. It bends, it stretches, it limits what we can see and do, and it connects us to the rest of the cosmos, from the smallest particles to the largest clusters of galaxies. So tonight, as you drift toward sleep, picture your own light cone, the bubble of events you can influence and be influenced by. Imagine it expanding into the future, shaped by your motion, your gravity, and the constant speed of light. You are not just moving through time. You are shaping it, carrying your own unique thread through the vast tapestry of spacetime. The journey through time we've taken together has stretched from the everyday ticking of a clock to the farthest edges of the universe. Along the way, we've seen how time is shaped by speed, bent by gravity, and bounded by the speed of light. We've discovered that the present is never quite the same for everyone, that the past is written in the light from distant galaxies, and that the future can, in theory, be reached more quickly under the right conditions. And now we arrive at perhaps the most humbling truth of all, that time is not separate from us. It is not something that flows past while we stand still. We are part of its fabric. Our motions, our choices, our very existence help define the shape of time in the universe. Think of every interaction you've had today. Each word spoken, each movement made, each thought formed is a point in spacetime, recorded forever in the geometry of the cosmos. You may never revisit those points, but they are part of the structure now, as real as the stars overhead. This is one of the quiet wonders of Einstein's view of the universe. Spacetime is a single entity, and time is just one dimension among four. From this perspective, the past and the future are not gone or unborn. They are simply places in the landscape of the universe, connected to the present by paths you can travel only one way. If you could somehow step outside that landscape, you might see your whole life laid out at once, from your first breath to your last. You would see all the moments in between, fixed in their places yet alive in their own frames. The you of yesterday is still there, thinking, feeling, moving forward. The you of tomorrow is already waiting on the path. For now, though, we are bound to move forward at the speed set by nature, 1 second per second, and to experience each moment as it arrives. And perhaps that is as it should be. A life lived all at once would have no texture, no anticipation, no change. The unfolding is part of the meaning. In our exploration, we have also seen that time's story is not just about physics. It's about perspective. A day on Earth is not the same as a day on Mars, or near a black hole, or aboard a starship racing between the stars. Time is local, personal, and shaped by where and how you exist. We have learned how cosmic expansion changes what we can see and know, hiding parts of the universe forever beyond our reach. We have touched on the mysteries of entropy and the arrow of time, and on the possibility that the universe's ordered beginning is the key to why time flows at all. And we have considered the boundaries, the places where our current knowledge falters, where quantum theory and relativity refuse to join hands, where the fabric of spacetime may be grainy rather than smooth, and where new theories could reveal that time is not as fundamental as we believe. It's worth pausing here to remember something important. The discoveries we've talked about did not come easily. They were built on centuries of questioning, testing, and refining ideas. They came from people willing to doubt the obvious, to follow strange predictions, and to measure what seemed impossible to measure. The idea that time slows with speed or gravity was once just a mathematical curiosity. Now it's measured daily in satellites, spacecraft, and experiments on mountaintops. The stretching of light from distant galaxies was once a mystery. Now it's a map of the universe's history. What will seem obvious to those who live centuries from now? What will they look back on as our greatest misunderstandings about time? The only way to find out is to keep asking, keep measuring, and keep imagining. And yet, for all the vastness of the topic, time remains deeply personal. The seconds between your breaths are as real and as valuable as the billions of years between the first light of the cosmos and the cold darkness that will come long after we are gone. Physics may describe time's mechanics, but living gives it meaning. So as you listen to the quiet now, remember that you are already a traveler through time. You don't need a machine to take you there. Every step you take, every sunrise and sunset, every laugh and every tear carries you forward on the only journey all living things share. Imagine standing beneath the night sky, watching starlight that began its journey long before you were born. Some of it comes from stars that no longer exist, their light still crossing the gulf between then and now. In a sense, you are looking at the past with your own eyes, not a memory, not a story, but the real light of events that happened millions or billions of years ago. And as you stand there, your own light is streaming outward too. Every moment, photons scatter from you into space, carrying the record of your presence. In the far future, someone or something might catch that light and see you as you were now. Just as you look back, others may one day look forward and find you. This is the quiet symmetry of time. We receive the past as light arriving in our present, and we send our present into the future in the same way. The exchange never stops, even if we are not aware of it. The speed of light, which we once thought of as a limit, is also a link, connecting every place and every moment into a single web of causality. It's the thread that holds the universe's history together. And so, as we close this journey, picture yourself within that web. See the connections stretching in every direction, to the people beside you, to the stars above, to the galaxies whose light is only now arriving. You are part of that structure, part of the unfolding story of time and space. The clock will keep ticking, the universe will keep changing, and you will keep moving forward, a traveler, a witness, and a participant in the great cosmic flow. Perhaps one day, long from now, humanity will learn to bend that flow more freely, to cross centuries in a heartbeat, to wander the deep past, or to leap to the far future. But until then, we have the most precious gift time can give, this moment here and now. Cherish it. It is yours alone, and it will never come again. Now take care of yourself and have a wonderful night.